All right, so before we start the presentation, has anybody in this room ever written your own buffer overflow attack? Raise your hand. Awesome, that's a lot more than I expected. How many of you have ever seen one demonstrated live? All right, well, all of you will be able to say that at the end of today. My name is Rian Quinn. I work for Assured Information Security out of Rome, New York, of all places. We do cybersecurity. Today, I will be presenting how to use your freestanding C++ in everything from Shellcode to UEFI, embedded systems, Unikernels. We use the approach I'm presenting today for our own hypervisor called Bearflank. If you're familiar with my talk in 2016 on how to run C++ in the Windows and Linux kernel, this is the logical extension to that talk. Also, if you got to see Ben's presentation, which was fantastic, we are going to take a very different approach to what he presented today. And if you're on YouTube, go watch it first. It was fantastic. Okay, so what's really the goal of this presentation? Well, we want to be able to run C++ everywhere. I mean everywhere. So no limitations at all. IoT, automotive, embedded is usually the use case people care the most about. But there's a lot of operating systems, frankly, that don't support C++. I threw ThreadX up there. I don't know if it does anymore or not, but I know for a while it didn't. Some systems just don't have any operating systems at all. You're literally writing applications for direct hardware. If you're writing your own kernels or unikernels, for example, include OS, you're going to have to do this. Or your own hypervisors, like what I usually work on. What about UEFI and BIOS? Have you ever wanted to run C++ from a UEFI application? Or shellcode and flat binaries. So a lot of the work I've done in the past has all been with flat binaries, and if you've ever attempted to do C++ in that environment, you'll know why it's so complicated. But shellcode is essentially written in mostly flat binaries. All right, so what does freestanding mean? Well, freestanding essentially means that you just don't have access to all the stuff you want. So, like Ben said in his previous talk before mine, you do have some things like standard int, standard defs, but they're really just definitions. There's really nothing useful in those libraries other than here's how I define an integer. So there's really no useful functions at all. There's no libraries. There's no C runtime support, which I'll get into a little bit. Surprisingly, that can be really frustrating. We don't have. In non-freestanding environments, there's just no way you're going to get flat binaries to work properly. And then sometimes you do need standard lib. Like I said in the description of the talk, one of the biggest problems I ran into when I started trying to get C++ to run for the types of projects I wanted to use is just simple things like dynamic cast and std-move don't exist without the standard library. I have no idea why, but that's the way it is. Exception support's another big one. You can turn all this stuff off. You can make ways of getting around all this stuff. But in the end, are you really programming C++? And you're certainly not going to be core guideline compliant if you do attempt to do it. Not using exceptions and not using the @ function and that kind of stuff means that you're just not guideline compliant at all. So I really wanted to find a way to fix this. Like how do I ensure that I can use all the same standard C++ functionality that I'm used to using, that I love, in my sort of freestanding environments where I just don't have access to this stuff. All right, so if you want to kind of do this yourself, you can start by grabbing LLVM's libc++ and libc++ ABI. And then, of course, you're going to need a libc to go along with this. And so you could use Newlib. This is not their actual logo. When I Googled LLVM's logo, this is what I got, so I had to put it up there. It's a My Little Pony version of their actual logo. My colleagues right now are like, oh, God. But anyway, this is how we started. We wanted to get all of C++, the whole thing, whole shebang, in a freestanding environment where these kind of limitations exist, and how do you make that work? This isn't easy. In fact, when we started, you couldn't really compile libc++ with Newlib at all. That's not a problem now, but it was back in 2016. So let's start with looking at the compilers, or sorry, the compiler flags, rather. Now, I want to keep in mind that as we go through this, like I said, we're taking a totally different approach to freestanding, okay? Most freestanding is essentially, hey, you get some facilities from C++ or C, but most of the stuff you care about, you don't get. We're trying to take the opposite approach that says, I have this freestanding environment, I want all that good stuff, because frankly, I don't want to rewrite std array and std vector and all this stuff, right? I want to use all that code. How do I do that? I want exception support. I want runtime support. I want all of it. How do I do that? So these are a lot of the various different flags you're going to need when you start. And we're going to leverage Clang for all of this. The reason we do that is that Clang's really helpful when it comes to the cross-compilation side of things. If you've ever tried to create a cross-compiler with GCC, you know the pain associated with having to recompile it just for every single target. With Clang, you don't have to do that. So I pretty much just use Clang at this point for that sole reason. You're going to need to find a sysroot. So you'll have to have some sort of folder somewhere that says this is where all of my stuff is going to go. And there are a couple quirks with this. When you want to try and compile LLVM and Newlib together so you can then run those in your sort of isolated environment, for whatever reason, ELF is needed. We're going to compile everything to the ELF standard, and if the target is, say for example, x86-64-ELF, for whatever reason, Clang doesn't include the ELF definition. I have no idea why. I'm just sure it's a bug. So you'll need to add that. Newlib doesn't provide long double support, and so we kind of toss in a flag in there to kind of fool Newlib into thinking that the long double is the same thing as a double. That needs to be addressed, and I'll explain that in the limitations of this thing later on. So that's a hack, and it needs to be removed at some point. There's also really no, from what I've been able to tell, there's no easy way to do this with standard ANSI flag enabled. So you're going to need to, one, enable GNU source, but you're also going to have to use the GNU 11, GNU 17 flags instead of the standard 11, standard 17 flags. And then libc++ does expect certain operating system support for things like POSIX, timers, threads, and even the clock. And I'll explain how that's all handled at the end, because that's got to be the first question everyone's asking, right? I'm in a freestanding environment for a reason. I don't have access to thread support. I don't have access to timers. How do I make that work in this type of environment? And I'll explain that. You're likely going to need fpic if you're on 64-bit nowadays. There are a couple additional ones that are useful. So, for example, no red zone. In my previous talk, I talked about the headaches associated with this flag. But if you're doing anything that's in the kernel level, like ring 0 below on Intel or AMD, you're going to need that flag, because otherwise you're going to end up generating code that's going to crash very quickly on you. And things like data sections and function sections are really helpful because they help reduce the size of C++. There's still some issues there. Now, granted, when I did some comparisons against C, that C today isn't much better. But for some odd reason, a simple main function with nothing in it, nothing at all, just to return 0, still ends up being about 300K, and I have no idea why. That doesn't make much sense. And that's even on like Ubuntu standard regular hosted environments. But it's also true in these freestanding environments. My guess is there's some sort of initialization logic, at least libc++, that's not being removed properly. There's also some linker flags that are needed to get this to work. So why static pi is needed, I'll get into near the end of this. But we're going, in this particular environment, we're going to try to leverage just static C++ executables. And pi is actually helpful. It's not a requirement. You can do this without the need for pi, but it can be really helpful. And of course, if you're going to be building a static pi, you want to add the no dynamic linker because there's no dynamic linker necessary. No standard lib is usually required, but also some helpful ones would include the last couple. I'm not going to get into what those do other than they just make everything smaller and a little bit more secure. All right, so on to the CMake flags. I documented this so that in case you guys cared, especially for pictures, you can see all this stuff. It's all on our GitHub page, so you can go and look at the source code and copy it yourself if you ever want to do this yourself. In the end, the only thing that we really care about here is telling libc++ that we're only building static libraries and what type of threading APIs we want to leverage. We're also going to turn off a lot of the newer features that make absolutely no sense in freestanding environments like the file system and some of the experimental stuff, which includes like networking. It just makes no sense at all. Even with some of the stuff we're able to do to get around the platform problems, you know, if you have access to an actual file system stuff, you're likely running on an operating system, in which case you shouldn't need this. All right, so what about Newlib? Newlib itself isn't a big deal to compile anymore. You will want to turn off libgloss. Libgloss within Newlib is the library that adds hosted support. And since we're in a freestanding environment, you don't need it. Same with multilib, that just prevents Newlib from compiling a bunch of stuff you're not going to use. And we're going to obviously tell it Clang. All the flags that we provided before go to Newlib as well. All right. And then there are some basic notes for all this. So when you're compiling all this software, you're going to be tempted to take the prefix include folders and add them into your compilation instructions. And if you do that and you try to compile libc++ more than once, it'll puke on you. So don't do it. That's the first one. And then once again, the no red zone. Basically what happens is with the red zone is the very end of a leaf function, its stack can be corrupted purposely. But in the event that an interrupt fires, you'll end up with actual real corruption. So you need this if you're running in something with interrupts. Question?
Have you looked at the interrupt stack frame things that are usually in PSSs on x86? They're meant to make red zone possible in kernel space.
Can you say that through the microphone? I'd repeat it, but I think I missed a part.
Yep. So on x86 64, there is a construct called an IST, which is specifically made so that any interrupt happening in kernel space will be triggered to move to its own stack space.
Yes.
And in that case, it will not corrupt your stack, even with the red zone.
Yep, that is true. Actually, we use that in Veriflink. So yes, the IST. Yes, that's helpful. That doesn't help in some instances. In particular, for when we were trying to get C++ running inside the kernel, that wasn't helpful because we weren't controlling our own stat or our own interrupts. So you couldn't use that feature. But yes, if you have that much control, you can do that. Okay, so what's missing? Well, the obvious. If I want exception support, I need an unwinder. That's a big problem. For C runtime support, a lot of people don't actually understand what that is. So let me spend just a quick second on it. If you compile with freestanding, you don't get a main function, usually. You get an _start function. That's it. Good luck. That's your entry point. Right? So how do you initialize global constructors and destructors in C++? Well, that's all done for you by the C runtime. Right? And then none of that's there. And oddly enough, inside some of those functions are things that actually do relocations for you during runtime, which is not documented anywhere I could find. But I certainly figured out when I wasn't doing constructors and things weren't working right. It's where your exception stuff is actually registered, so you got to do that too. And once again, if you want an actual main function, you're going to need to emulate that in some way. There's no POSIX thread support in this, right? libc++ doesn't magically provide pthread support. And what about system calls? Like libc++ and Newlib have no idea how to write to a file. They don't know how to write to a console. Something as simple as hello world is extremely difficult in a freestanding environment. You have to do it all yourself. Right? So how do we get around some of that stuff? And so I mean, essentially, you don't execute C++ without additional section information. To do all the stuff I just described, you need additional sections that are compiled as part of the executable that you need to provide your C code with access to. So things like .init, .fini, .ehframe, those are all sections that the compiler generates that your C++ is going to need. And in freestanding environments, you know, you could spend the time and write a linker script and put it all together and do all the work. It's a real total nightmare, and the chances you're getting it right are really small. This is what makes this so complicated and why freestanding environments usually prohibit the use of all of this stuff, because as soon as you attempt to try and turn any of this stuff on, it becomes a real problem. So the question is if I want to run C++ with everything, right, how do I get around this particular problem and be able to still work in a freestanding environment where I have access to nothing? Well, do I need an elf loader? the answer is no. Once again, you can do all of this yourself. I've done it. When you're done, you're going to realize you basically just re-implemented the ELF spec, right? And so why do it? Like, learn from my mistake. Don't do it, right? Just build an ELF loader. What you'll find actually is we already did that for you. And it's been done by many other people too. It's all over the place. So you should just use some sort of pre-existing file format. ELF is what we use for this. Most of the people working in freestanding environments are working with Unix tool systems. They're not working with Visual Studio. But if you need PE, you can do that too. Either way, there's data there that you have to get access to because it's not part of the regular executable that makes C++ run. Unlike C, C++ just has these extra dependencies that you need to include. All right, so this is our approach. And so basically, we did this under the Bareflank hypervisor for years. We wanted to be able to write a hypervisor in C++. That was the goal. And, well, really, actually, the goal was to write a hypervisor SDK that we could build other hypervisors from for research. We do lots of work with hypervisors, and we like playing with all the different types of things that are in there. I've personally written 4 of them myself, one in assembly from scratch. And after you've done it multiple times, it's like, oh, I just want to be able to do this very quickly. And so the point of this project was to do that. But we also wanted to use it in very mission-critical type systems, and C++ was the better option because, well, frankly, it's a safer language. And so we were like, all right, well, this is great. We want to leverage C++, but how do we get access to all these facilities that ensure that we're doing things that adhere to things like the core guidelines, but really also allow us to leverage the facilities of C++ that go above and beyond just the language, but also the library itself. And so we built this. We've been using it for years, works great, and we even presented it at one point. After we presented it, we got just inundated with requests for how do I do this in my own environment, right? I don't care about running stuff in the kernel. That seems pretty weird. I don't know why you're doing that, but I personally want to run it in this environment. I want to run it over here or whatever. And so finally took the time to take all of that stuff out of our project and put it into a separate project that you can now leverage. It's all open source under MIT to include C++ in any environment that you want very easily. It supports C++ 17, which is the latest and greatest LLVM stuff, and it's using 9 right now. It has full support for C++ exceptions. I actually wrote a custom unwinder for it. Eventually, we may end up using Apple's instead, but for now, it does have its own unwinder. And the actual ability to load this application in the freestanding environment is done with a custom ELF loader. Very simple. It's header only. The real benefit to ours is the fact that it's header only, and it has really the only dependencies are things that the freestanding environment is guaranteed to have. And so you can essentially run this ELF loader from any environment, which we'll show here in a little bit. All right, so how does it work? Well, there's no easy solution to being able to take a freestanding piece of code and add all this other stuff that's not supposed to be there. What we found is that works really, really well is that you have this thing what we're calling, which in the slides I called it the C loader, but the C loader is really your freestanding piece of code. It can be freestanding C++, freestanding C, it doesn't matter what it is. But it's this application that you have to run somewhere. In the case of the 2 demos we'll show today, it could be a UEFI application or it could be shellcode for buffer overflow attack. Whatever you prefer, you can do. It's the thing that's freestanding. Then from there, it then turns around and loads the C++ application into itself. And that C++ application has all of the things that it needs to operate properly. It has its unwinder, it has the C runtime logic, it has libc, it has a method for doing system calls to handle device type stuff. It's all there in a nice, easy to use environment. And both are actually compiled with freestanding. Now the reality is the C loader can be compiled any way you want. And for a quick test, it's just a C application that's hosted that we just then run C++ in and use. Once again, if you can get it working in a really limited freestanding environment, you could pretty much make it work anywhere. So let's talk about the C++ application when you're using this approach that we have here. So you gotta start somewhere. So let's start with hello world. Oddly enough, behind the scenes, and there's actually another talk that about back to the basics that talks about what it takes to make this work. Right? So I highly advise watching that one because this is really complicated. Right? It's like the example we could teach everybody, but they have no idea how much work went behind to make that work. And so we're going to start with this, and we have to have some way to compile it. And so if this project's to be of any use to anybody, it's going to have to be simple to compile against. And so we make heavy use of CMake. When I presented back in 2016, it was all custom make files. So we graduated, and now everything's all CMake. I don't know how familiar everybody is with CMake, but this is pretty much your typical CMake type build script. The only addition to the build script that you might not recognize is the find package function and the target link libraries function. So the find package says, please go find me this thing called standalone C++, and the link library says, okay, once you find the package, please link against it. And that's it. All the work is done for you behind the scenes. It figures out what libraries need to be linked to your application. It ensures all the right compiler flags are there. It ensures all the linker flags are there. Everything is there. The only strange thing that we still have to do, because I don't have an easy way of doing this today with packages, is you'll still have to define your tool chain and your prefix. So when you compile the standards or the standalone C++ project, it will ask you to put it somewhere. It'll create a prefix, which is once again that place you put all the stuff, all the libraries, include files, everything you're going to use. And so you have to point it to that, because unfortunately I don't have a great way of automating that. And then the tool chain, that's still required. I'd like to get away from that at some point. I think it's possible, but I haven't figured it quite out yet. So once you do that, you can build against your little script there and run make, and you'll get a hello world. It'll spit out. So that's all you have to do to create a C++ application in this environment. Okay, but there's still the loader part. Was there a question? Question? Okay. So there's still the loader part that we got to worry about. All right, so I got the C++ application. I want to now run it in my freestanding environment. How do I do that? And so once again, like I said, the loader itself is pretty much anything that you could think of. I say freestanding because that's usually the environment has nothing. But frankly, it could be anything. So UEFI, for example, is not technically freestanding. I mean, it is, but it's got a lot of stuff that it provides. So for all intents and purposes, you can do a lot of things in UEFI that you wouldn't normally be used to in a freestanding environment. Versus, like, for example, Shellcode, where you have nothing, literally nothing. But you might want to create like a legacy BIOS bootloader. So if you're building a Unikernel and you want to run a real hardware, or you're running a Unikernel on a hypervisor that still emulates BIOS, then you might want that. If you're building a C++ in a kernel module like we like to do, then you might need that. There's a bunch of reasons, but whatever it is, the loader is the thing that's it's kind of like your entry point. In our environment, another way of looking at it is the loader is the thing that runs bfexec. And so bfexec is like execv. It's just our version of it. The parameters are slightly different, which I'll explain, but it basically does the same thing. It runs some sort of application. So let's look at the UEFI example. So I'm going to assume that nobody knows anything about UEFI, so I'll step you through a little bit of the details. This is what a UEFI entry point looks like. So instead of the main argv or argc argv signature that everyone's used to, in UEFI, that's what it looks like instead. But it's the same thing. And the initialize lib thing you can ignore. That's a UEFI-ism. The only thing we care about is bfexec. bfexec is the thing that's going to run our C++ application. This cxx UEFI and cxx UEFI underscore length I'll explain in a minute. And then there's this sort of pointer to a functions thing, which I'll explain. That's it. So you have bfexec. You have these three sort of oddball things that you provide it. That's all that's needed. Okay, so let's start at the headers. You have your UEFI normal stuff. You can ignore that safely. And then there's bf alert. So our bfexec sometimes needs to output errors when bad things happen. And so bf alert is what's used to do that. Once again, this is freestanding. So like I said before, printf and cout don't exist. And so whatever environment you're in, you've got to provide that. And so in this particular case, that's what printf looks like in UEFI. It's just print, and everything's 16-bit wide characters. But it's totally possible that you may not have a print function, in which case you can just leave that macro blank, and it'll just blank out all the printf statements inside the bfexec. So, debugging is going to be a total pain, but it'll work. You can also use that in release mode to get rid of all the extra stuff so that you don't have it there, to reduce the size of whatever it is you're doing. bfexec is the header-only include that you need. Question? Oh. And then cxx UEFI is this magical little header. So there are many different ways to get your C++ application into your freestanding environment, right? So in this particular example, I'll show one way. In the shellcode example, I'll show you another way. Here, what we did is we took the C++ application, which we just compiled, that generates an ELF file, and we use xxd to convert it into a header file. And it literally creates one giant header file with all the bytes for that EFI filled into an array, and it gives you a pointer to the array and its size. The compiler then takes all that crap and puts it into the data section of your executable, usually. And so that's one way to do it. It's not a great way, but it works. Works really well, surprisingly, for most of the stuff we care about. But there are other better ways to do this. You could, for example, in your freestanding environment, use a linker script to place the executable somewhere in your freestanding code, and then actually use a linker script to get access to your pointers and lengths and do all the calculations and all the fanciness. So that would work too. There are many different ways that you can get it in there. It's up to you. You could also just open a file and allocate a memory buffer and do all that. My guess is if you have access to all that kind of stuff, you probably don't need this in the first place, but if it is there, sure, you could do it. So if we go back real quick, we look at that signature, we now understand the first two, right? So xxd produced a C-style array in a header file that has all our C code embedded in it. So the last part is this function thing. So if you're a Linux programmer, this will be really familiar to you. This is essentially how the entire Linux kernel works. You got just all these callback structures that you fill in. So this is essentially the same thing. There are 4 functions that you can define. Only one of them is required. And hopefully over the next year or so, we can remove the requirement for that one too. And so there's alloc, free, markx, and system call. So let's get into each one of these. All right, so alloc. So right now, the way it works is the bfexec will go and allocate a buffer and then put that C++ application into it using the ELF loader. Okay, so you can't just go and execute the ELF file. You actually have to load the ELF file into some memory and then execute that memory. If you don't do that step, then there's a bunch of stuff that's missing. And more importantly, likely the layout of your memory is not proper unless you did some really fancy linker script stuff. So the ELF file itself tells you how you're supposed to put it in memory, and that's what this step is doing. Now, eventually what I want to do is get to the point where the ELF file can be used or the ELF loader can be used at compile time. It produces the memory layout, and then you can shove that into your executable using the linker script or the xxd or whatever you want. So that part can be done not at runtime, but at compile time. But for now, this works. And keep in mind, too, that the allocation of memory, there's this, we're going to execute from it, and so execute permissions is going to matter. And so I'll get to that in a little bit. But in most freestanding environments where you're working in embedded systems or whatever it is, you can just allocate memory. It's always marked read, write, execute, and you just do what you got to do. That's not always the case. In UEFI, this is essentially how you allocate a buffer of bytes. Free is self-explanatory. I don't think I need to explain that. It's the reverse of alloc. It's optional because you don't have to free memory. You can just leak it. So if you don't want to use it, your problem. Same thing. So you can implement this any way you want. So this is an example of using C functions that exist. So alloc, lined alloc and regular free. It's whatever you need to use in your environment. If you don't have dynamic memory allocation, then you can just allocate one giant buffer and then use something like SBRK, for example, that type of memory allocation where it's just essentially a moving window. And you can just start blocking out chunks that you can give to it. It only has to allocate 3 things, so you don't need a lot from it. And so once again, if you don't have dynamic memory allocation, this isn't, free and malloc isn't being used to create all these little things all over the place that's going to get lost everywhere. It's creating 3 buffers, that's it. And like I said, at some point we should be able to remove the requirement for that and do it all at compile time, since it really is that simple. The mark Rx function is needed because, once again, not all systems mark all of executable or all of memory that you allocate as executable. So what's supposed to happen is when you malloc memory, it's marked read-write, and you have to explicitly mark it read-execute if you want. And it should actually never be read-write-execute. That's what causes so many problems. So if you happen to be on one of those environments, you'd have to implement that. In the case of UEFI, we don't, so we just leave it blank. You could also fill in a null pointer for that if you wanted to, within the structure. Once all the optional ones, you can do that. But once again, if you're on a system that does do read-write protections properly, then you could use something like mprotect or whatever the facilities are in your operating system. Or if you're like me, you would probably just parse the page tables and mark them yourself. Last but not least is the system call function. And this is where all the sort of magic happens with respect to the device stuff. So if I do std cout in C++, where does that go? Well, in the end, what it really does is it makes its way through all the C++ code, which is surprisingly complex. Once it finally gets past all that, it eventually makes it to a libc call called write, at least on Linux, and that actually writes to a specific file number that's dedicated to console out. And so in that case, it's usually 1 or 2, depending if it's std out or std err. And so when you compile libc++ with Newlib and you don't include libgloss, there's a series of functions that Newlib purposely doesn't implement because it's like, I don't know what to do with those. You have to provide them. And so what we did inside of our project is we implement all of those functions, and all they do is they make a call to the function that you point to with this function pointer. So when libc++ attempts to make a call to write, it packages all the information up associated with that and makes a call to this function and says, okay, the ID is, syscall write, and here's all the arguments for it. You do what you got to do with it. And so on UEFI, for example, I'm going to print all the bytes out to the console using print. And I do that stupid method because I frankly couldn't figure out how to do the conversion of 16-bit wide characters to 8-bit ASCII characters. So that works. But at any rate, all of those types of weird functions that are needed, you can implement or not implement. So it's totally up to you. It depends on the environment. If you are in an environment where none of this is there and you're writing all of the device stuff yourself, or if in the case of like a shellcode, you don't really care about device stuff, so you're just not going to do it anyway. It's entirely up to you. You can make it as complex as you want. You can write all the device stuff right in C++ and do everything directly from there, or you can let our code forward it onto this part where the loader can do it, because maybe it has an environment that does provide some of these facilities, like, for example, EFI can print to the console. It can also write to a file. It can do all sorts of different things. So I could fill out this function as much as I want and get as much functionality as I desire. But this provides that sort of missing glue above and beyond the unwinder that we provide and the elf loader and all that kind of stuff that's needed to make this stuff work, and the C runtime, all of that. That's all done automatically for you. This is the only part that's not, because we really honestly have no idea what you want to do. All depends on your environment. All right, let's do a demo. UEFI. I have no idea what's going to happen because I have to reboot my computer to do this. So, yeah, if it doesn't work, that's what it's supposed to look like, sort of. It actually doesn't say that, it just says hello world. That's an old one. But this is the demo we're going to show. So I'm going to reboot. We're going to see if this works. If it doesn't, we'll move on to the next one. But have you ever seen anybody reboot a computer in the middle of a presentation? I'm going to go back in and we'll just continue. So if you want to see all of this yourself, that UEFI example, then you can go to our open source project and download it, compile it, and run it yourself. But what you would have seen is me just run a UEFI application, and it would have printed hello world, and that hello world was coming from a C++ application. And so using all the stuff I just showed you right there, I was able to compile a C++ application into my UEFI environment and execute that C++ without a problem. So let's look at our simple test case. You can see that. All right, we're just going to do this for a second. All right, so if we look at this, make quick. This is the C++ application running from a, like I said, just a regular good old-fashioned hosted C, as a test case. So to kind of show you what this looks like, if we go to tests, you can see this code here. And this is actually a relatively complex little hello world example. So to start, there's exception logic. There's a static class instance, okay? And it was talked about briefly in the previous presentation, but if you want to be able to do static type stuff, you're going to need not just global construction destruction support, but support for @exit. That's where the magic occurs. Whenever you do a static definition, it registers the definition with the @exit function, and that's where the destruction occurs. When you call exit, exit actually goes and runs through all the registered statically defined objects and goes through and runs their destructors. And so to prove that all that logic is glued properly and working, we create two different classes, one that has a constructor and does something, and one that has a destructor and does something, and test to make sure that all of these work. And so we also use a std array just to show that the standard library does what we want it to. It all just works. So that, the idea was to try and create something that was more than just a hello world to prove that we didn't just make printf work. It's the full facilities of C++ all working in front of you. And so the loader in this particular case is, you'll see that the same logic. So you have your allocation function, your free function, your mark x to mark the pages properly in your syscall. And this is, once again, just calling write because I'm running it on regular C++, and so, I'm running on Linux, and so therefore I have access to it. So that works. This function here, map file, you'll see in the next example, it actually takes the C++ file and maps it into the application, then I use that. So instead of using xxd, this is how we're doing it, just to keep it simple. So this is how you map a file in C essentially, but we did it in C++. And then it just runs the bfexec function and then cleans up, nice and simple. All right, so let's get to the more interesting example of running the shellcode stuff. If I can get this monitor working properly. Yay, we're back. Okay. So before I do that, let me pull up the slides. There's one more diagram I'm going to show because I think this will help with explaining how this stuff works. All right, so I don't want to turn this lecture into how to write, attacks, because frankly, you could spend multiple presentations on how to do this stuff. But I will say that the demonstration's based off the original stack smashing paper. There's some additional things you have to do because times have changed. But in general, the way the stack works on the Intel architecture is the stack actually grows up while all your data grows down, or it's the other way around. Either way, I just know they're backwards. That's what I remember. And so if you look at this diagram here, if I've got a buffer, okay, so it's just some character buffer, and it has this particular size, and I define it at the beginning of a function, and I go and then read through the buffer. If I continue to read past the bounds of the buffer, I start reading my stack. And so you're going to run into other variables that are defined in that function, and eventually you're going to run into the return address for the function itself. And so the way a buffer overflow attack works is that you load the buffer with a bunch of stuff that's your payload, it's your attack, and then you keep loading beyond the extent of the buffer until you hit the return address. And at that specific spot in the return address, you populate it with the address of the stack itself. And so when the function attempts to return, it goes to that return address to get where it's supposed to go, and instead of it returning to wherever it was meant to go, instead it returns to the top of the stack, where you put a whole bunch of executable code. And so then it starts running through all your stuff instead, right? So that's how this works. That's the basics behind it. Once again, if you're more interested in the really crazy details, there's a great paper called Smashing the Stack, which is based off, like, kind of did all of this. And go read that. It's a great read. All right, so let's look at our payload. So our payload is the thing that's freestanding. It's the thing that has no environment. So literally, we're trying to compile a piece of code that we're going to stick on the stack somewhere, and we're going to execute it. We don't have any operating system to rely on. We have nothing, absolutely nothing. It's just an executable. We stay freestanding because there just is no facilities there for us to run. And so we'll start by looking at the same old stuff. We have the allocation function, mark x, system call. There's no free because we're attacking, and anybody who builds an attack and actually frees memory, that's just no fun at all. So the first thing you might say to yourself is, well, what is this external malloc? What is this external mprotect? And so I'll get to that in a second. But keep in mind that in my environment, there is no actual malloc or free or anything like that. I have to get it from something else. And we have our same system call, so we can go and write to a buffer, but same thing, it's this external write thing. I don't have anything there. I have my functions. And then from here, I have this little block. Now, the actual start function is actually here. And so when you're in a freestanding environment, that's what start is. That's your actual entry point, usually. It's not always, but it usually is. And so in this particular case, I can't just go and execute my code because it's going to need a stack. This is where we deviate a bit from smashing the stack. They go and really kind of hard code all the byte logic that goes in there. We wanted to make this really simple because we wanted to be able to run C++ and do whatever you want in that environment. So to do that, it's going to need a legit stack. And so the problem is that the stack pointer is now all combobulated because we're messing around with it to do the attack itself. So the first thing we do is we basically move the stack pointer way, way up so that we're not colliding with ourselves, and we've got space above to go and add actual stack stuff that we're doing. So that's what that does. And then it just calls C. Which, like I said, so that's here. And all this does is it opens up the C++ file that we want to run inside our shellcode, and it gets its size, it actually maps it in, and then it runs bfexec. But same thing. There's this external open, this external file size and file map. Those aren't even standard functions. And there's this external exit thing. The only thing that's not marked external is bfexec. All right? So all of that external stuff is located here. These are just function pointers, essentially, marked with this deadbeef stuff. And so what I did to make all this work is I take the executable that I'm going to hack, and I analyze it to get the actual virtual address of every function I need in my payload to make this functional. And so because the application I'm running happened to have been compiled statically, and it also happened to be compiled with ASLL turned off or with an executable stack and all these lovely security features that would never be turned off nowadays. This one just happened to have it all turned off. I can very easily now just go to the application and say, hey, where's open located inside your app? Where is write located? And I can get the actual virtual address, and then in a post-compilation stage, I can take this payload, and everywhere I see deadbeef01 inside the code, I just overwrite it with the actual virtual address of open. And wherever I see the next one, I do exit and malloc and all that. And so before you're done, you have a payload that actually has access to some of these functions that belong to the application you're hacking itself. So you're going to use the application to perform the hack in addition to what you're doing. So kind of a neat little approach. And finally, the last part of this is we define our BF alert just like before. We're using external fprintf because oddly enough, printf wasn't in the application, so I had to make it work with fprintf. And there's this fancy little stack thing. So we use a custom linker script to compile the whole payload. And then at the very end of the payload, so the payload itself is the actual size of the buffer we're going to attack. And at the end of the payload, we have some padding because there happens to be some additional variables that it's doing, so we got to get past that. And then there's actually a push to RBP, which you should actually see in pretty much every function, at least in every function compiled in debug mode. So there's some of that. And then eventually there's the actual return address, and that's where we fill in the return address that we're going to go ahead and hit. And we also get that from the application as well. And so when it's all said and done, the linker script and the post-compilation phase produces this binary blob that's about a page in size. That's actually about 2 pages in size. And that binary blob matches perfectly with the thing I'm about to attack that will fill in the buffer that we're going to attack with our executable code and then overwrite the return address so that it points back to that buffer and then executes our logic. And that's it. That's how that works. So I can run this little executable, and all it does is it's just this executable here, and it takes 2 parameters, one file and another file. And it just takes the 2 files and compares the 2. If they're equal, it spits out equal. If they're not equal, it spits out not equal. It's that simple. It just so happens that the way that the application was written is they forget to check the size of the buffer, and so therefore it's easily overflowed. Sounds stupid, but it happens all the time. It's like all the time. It's why things like the core guidelines are so important, because they don't allow you to make those mistakes in the first place if you adhere to them. And there's tools to tell you if you're adhering to them. So I can run this. All right, so you get to see a little bit of magic here. I was worried that a reboot would do that. So if we go to the file compare, I can, from here, this is the actual function. And the way that you can, like, you know, play around with these things is actually to modify them yourself. So all I'm going to do is say, hey, where's the location of the buffer? So now if I run this, it'll tell me, oh, that's why. I forgot to run that first. This is that post-compilation phase that you got to do. And the reboot turned ASLR back on. I got to turn it back off again. Once again, don't do that for real. Okay, so there you go. And so that little printf is still there that I just put in there. But as you can see, the equal, not equal shows up. And because my attack is obviously not equal to the file I was comparing it against. And then it prints out that whole giant C++ application again. So there's C++ running from shellcode, from a buffer overflow attack. And just for the curious, if you look at the address that I printed out before and after, the address that's there is all sorts of gobbledygook. And this one is very, very specific. It's got a lot of F's in it, right? That's ASLR at work. So ASLR produces a random address for the stack. Without ASLR, you get the same address for the stack over and over and over, which is what allows you to create these types of attacks. But there's all sorts of other things that are added to it as well. All right, so just to finish up here, one last slide. What are the limitations? Well, right now it only supports Intel AMD on 64-bit. We have no plans to support 32-bit. If somebody really wants that, maybe, but we do plan to add ARM and MIPS. So then position independence is also something that at the moment we currently require that can be removed, and we actually want to remove that. So static pi is required. We want to get to static non-pi. Support for shared libraries, we have no intention of supporting. And it's odd actually to watch the community move, because like GCC and stuff are kind of moving away from dynamic shared libraries because they have their own problems now. So it's kind of interesting to see where that debate ends up heading, because like Go at the moment is all static, but you know, so everybody doesn't like that, so I don't know. It'd be interesting to see where that goes. But at any rate, we don't plan on providing support for shared libraries. Anybody who actually uses that likely already has an operating system to do it for them, so why would you do that? Being able to compile in Windows is something we want to do. That's going to require a new libc to make that work. Newlib doesn't compile in Windows unless you use Sigwin or something like that. And pthread support. So actually being able to run threads is something we also want to be able to support. It won't look like what you're used to. Thread support and an operating system has a scheduler and there's clocks that are needed to make that work. And in this particular case, the thread support would be more like, okay, I've got something running, I want to yield to something else, and whatever it is you're yielding to has to yield for the next thing to be able to execute. So there's no like interruption type stuff going on, but it's still actually quite useful to have the ability to do that. So that's something we want to do. And then we are going to probably want to implement our own libc and get rid of Newlib. It's no diss to Newlib. That project's been fantastic. It's just not really well suited for the stuff we're trying to do, and we've really battled a lot with it. So we'll probably end up doing something else at some point. Okay, any questions?
Hi, I'm wondering what approach do you support for exception handling, either table-based or frame-based?
Well, table-based or frame-based?
I mean, table-based is when you generate a special table where all information about exception is
Thank you.
which
Yes.
contains all this information.
It is table-based.
Frame-based is usually implemented using setGMP and longGMP.
Yes, it is table-based. And so once again, that's why we need some form of like file format that can actually do that, right? So we compile the ELF. ELF gives us the tables that we need. The C runtime in this project is hooked up to know where that information is and then leverages that within the unwinder.
And how do you unwind the stack? Do you use the stack unwinding tables, or you use frame pointers maybe?
We use our own unwinder. It actually uses the dwarf tables that GCC will put into the ELF loader or into the ELF file. So there is an actual .eh_frame table that contains all of the information to unwind the stack from function to function to function in compressed dwarf code. And then we actually built an unwinder that will do all the decompression and actually unwind the stack. So it does use the zero overhead implementation. The only thing that we don't use at the moment are the EH frame. There's another table that gives you a hash table essentially. We don't use the hash table. But frankly, I've never cared so much about the hash table because in the end, I don't really care if exceptions are slow. They should never happen, ever, right? So I don't care if they're slow. I just care that they work. So when an exception does happen, I need it to be reliable. So we do have plans someday to probably move to the Apple's unwinder. I think it's libunwind. I mean, there's like actually 5 different projects called libunwind, unfortunately. Apple's is no different. But the problem that all of them have, including Apple's, is that they all have OS dependent stuff in them. And so we wrote our own because we wanted to get rid of that. In the end, we probably could actually go and remove all of that OS dependent stuff out of Apple's and then be able to leverage it here. But it's complicated. There is some stuff that would have to be done to make that work. Did that answer your question?
Yeah.
Okay. Any other questions?
I can ask one question, yes.
Go ahead.
It's about your approach to implement system calls using shellcode. And I'm wondering, why don't you write your own wrappers around assembly instructions to execute the system call? For example, if you know operating system, you can just run int 0 or 08h and with some preceding instructions to execute the system call. Why don't you do this?
This took me about a couple hours to write, so that's the first reason. I didn't feel like writing all the assembly to do the system calls manually. You could do that, frankly. However, most people don't use ints anymore. They use fast system calls in 64-bit, so that's a bit more complicated. You'd have to know a little bit more about the ABI, but it's either way, with fast system calls or interrupt-based, you could do either one. And yes, from the shellcode, you could do that and not have to get access to any of that stuff, and that would simplify things to some degree if you had the time to go and write all that. But it would work. There's a little bit more of a complication in the sense that there was some fanciness I was able to do because the application that I was hacking happened to have, just so happened, I wrote it, some functions that made things easier. So leveraging that was nice, and you can't do that with system call stuff. But yeah, what you're saying, you can definitely do. Frankly, there's a million different things that you could do to make this more impressive, including like doing it so you don't need all the security features turned off. But once again, I wanted to keep it somewhat simple. Any other questions? All right, well, thank you very much for your time.